Okay, so today we're going to continue finishing up talking about our venules and veins. Then we're going to move into talking about lymph and mean arterial pressure and its regulation. But before that, we got a short little review question. So hopefully we did a little bit of chit-chatting about this. So we're not looking for an exhaustive answer, but we wanted to jog our memory about what happens in our cardiovascular system when we have a situation where we're panicking, running away from something. So in this situation, hopefully these are a couple of the things you discussed. All right, so in this situation, we know a specific part of our nervous system is active. So that's going to make a difference. All right, so we're going to have our sympathetic nervous system activated in this fight or flight situation. So some of the things that we know from ANP1 that are going to affect our cardiovascular system and therefore our vasculature, and therefore as we move into mean arterial pressure today, we're going to see this making a difference as well. So we know our heart rate is going to be up. Our ventricular contraction is going to be up in response to our sympathetic nervous system, meaning overall we have a rise in cardiac output, so in blood coming out of our heart. Some other things that we might be thinking about would be local, so intrinsic versus extrinsic effects on the vasculature. So if we're thinking about our tissue, we're thinking that we're running away, we might be thinking that we are metabolically active there. So locally, we might have some active hyperemia going on near that skeletal muscle. So that skeletal muscle is using a bunch of oxygen, producing a bunch of carbon dioxide that's accumulating in that interstitial fluid. And we know that that has an effect on arterioles. Specifically, this means that those arterioles will dilate. So we're going to have vasodilation. And therefore, we're going to have an increase in blood flow due to that decreased resistance under those vasodilation conditions. We might also have been thinking about some of the extrinsic effects back kind of to that sympathetic nervous system. So we know that the sympathetic nervous system releases norepinephrine. So we talked a bit about adrenergic receptors, right? So we know that we have alpha receptors, alpha adrenergic receptors throughout the body. Norepinephrine binds to those, and that causes vasoconstriction. When our blood vessels constrict, their radius gets smaller, so our resistance goes up. Okay, so we'd see a rise in TPR, and we'd see a rise in mean arterial pressure at the same time. We might also be thinking about epinephrine or adrenaline coming from the adrenal glands, also related to that activation of the sympathetic nervous system. This would bind to beta-2 receptors, which we see specifically in cardiac and skeletal muscle. So those beta-2 receptors, instead of causing vasoconstriction, they cause vasodilation in those specific regions. So as we have vasoconstriction in the rest of the system, vasodilation in cardiac and skeletal muscle, we're going to increase the amount of blood flow to the heart and skeletal muscle. Okay. Elsewhere, epinephrine is also binding to alpha receptors, but that's just increasing that vasoconstriction effect that we had with the norepinephrine as well. That's what I got. Anybody come up with any additional things that might be going on? This is not exhaustive, but this is how we kind of apply some of these concepts we've been talking about to situations you might actually encounter, depending on where you go on spring break. I'm from Jersey, so my family always drove down to Florida. Cool. So think about these in your daily life as you are thinking about your cardiovascular system. Try to think about what's going on in your body. Makes this a little more fun than just memorizing things. Okay. So where we left off last time, we were talking about veins and venous return to the heart specifically. So you didn't have this image. I just pulled it off of Google Images to summarize what we did last time. So we were talking about how we have two kind of pumps that allow us to squeeze veins essentially and change their pressures in order to help pump against gravity and return to the heart, because we don't have very much pressure in those veins from the blood. So one of those was the skeletal muscle pump, which is dependent on skeletal muscle contracting and relaxing. And that contraction raises pressure, pushes blood back up towards the heart. When your skeletal muscle relaxes, we have valves in those peripheral veins, so it can't fall back down. And the other thing we talked about was the respiratory pump, which requires us to think a little bit about pressures and what happens during breathing. So that's a little harder because we haven't done our respiratory system yet. So what we wanted to know was that the thorax, where we have our lungs, and the abdomen basically occupy the same overall chunk of space. So they're going to trade off. If the thorax gets bigger, the abdomen gets smaller, and vice versa. If the thorax gets smaller, the abdomen gets bigger. So this means we can change pressures and relative pressures in the thorax and the abdomen. So when we breathe in, what we're doing is making the thorax bigger. When we make a container bigger, initially what that does is create a drop in pressure. So that drop in pressure sucks blood from the abdomen, where we have the pressure increasing, because this is a trade-off. They're doing the opposite of each other. All right, so thorax pressure goes down, abdomen pressure goes up. Blood follows pressure gradients, so blood travels from those veins in the abdomen into the thorax. And then as we breathe out, we decrease the size of the thorax, so we're constricting our lungs essentially. So the pressure is increasing there in the thorax. We might think that that would push blood back towards the abdomen, but we know we have controls on a sort of unidirectional blood flow. So what happens instead is, as we have pressure building in the thorax in those veins, it's pushing the blood into the heart, increasing our venous return to the heart. So that's where we kind of left off. Okay. So now we want to think a little bit about another factor relating to veins, which is our blood volume. So we know that veins have high compliance. So we think about them as a volume reservoir versus our arteries, which had low compliance, which we think of therefore as a pressure reservoir. However, we do have changes in pressure to some degree when we have changes in blood volume. So even though veins are highly compliant, if you increase the blood volume, you will increase venous pressure, just not as dramatically as if you put extra blood into an artery. And when you decrease blood volume, so you get super dehydrated or you get some type of laceration and you're losing blood, that's going to cause a decrease in venous pressure. So we do have changes in venous pressure depending on how much volume is in those veins. And this is important to realize because as we talk about mean arterial pressure, which is basically blood pressure, we are going to be talking about some short-term regulatory effects. We're going to be talking about receptors that sense pressures, make adjustments. But when we think about long-term regulation, rather than sort of initial reactions from your body, long-term regulation is going to happen by regulating blood volume rather than by regulating constriction and resistance in your vasculature, which is what we will spend a lot of time talking about when we talk about mean arterial pressure. So long-term regulation of blood pressure is important, going to occur through regulation of blood volume, which is in the veins. Okay. So veins do have a little bit of venomotor tone. So they have a little bit of smooth muscle. We're not thinking of them as really changing their resistance much. But when we think about that smooth muscle in the wall, tone is just like a slight degree of contraction, right? Sort of at all times we mentioned. So what's going to happen when we change that venomotor tone is we're basically going to be changing the compliance of veins. So I pulled from an earlier slide just a little picture of compliance because pictures help me think about things. right? So we remember that compliance, we're talking about a pressure and volume relationship. So something that has low compliance has a relatively high pressure with not very much volume. Something that has high compliance, that same pressure is going to include a lot more volume. So what we're saying is that with increases in venomotor tone, we could change how high that curve is for our veins. So if we have a contraction in the smooth muscle in the wall of a vein, we're going to make it a little less compliant, essentially. So what we're saying there is that wall is no longer quite so floppy, right? And because that wall isn't quite so floppy, we might change the curve to something like that. This is not a real curve, but that's what we're saying. Okay. So when we have an increase in venomotor tone, what's happening is the smooth muscle is contracting a bit. That's what we mean when we say that. And this is a reaction to the sympathetic nervous system in part. Okay. And this comes back to that norepinephrine coming from the sympathetic nervous system. And specifically, we have alpha adrenergic receptors that are causing that venous constriction. So a takeaway here, we mentioned alpha receptors a couple times just now in that little review scenario, and they're coming back here. So your best bet is if you're looking for a receptor relating to our vasculature, you're probably thinking about an alpha adrenergic receptor. The only time we're thinking about those beta-2 receptors is skeletal muscle and heart. Okay, so alpha receptors should be your go-to. The beta-2 receptors are like your exception. Okay, so as we're decreasing this venous compliance, we are also increasing a little bit the central venous pressure. So the pressure in those veins in the abdomen and going into the thorax. And overall, we're going to have this situation. We're increasing venous return. And when we say venous return, we mean venous return to the heart. Okay. That part is implied, so it'll just say venous return on all your little flow charts, but we're talking about venous return to the heart. Okay, so we're gonna walk through a flow chart of that now. Okay. So our ultimate goal is to understand our effects on mean arterial pressure. So essentially a sort of measure of blood pressure, because that's going to be our next major topic. But we're starting just with the effect coming from the veins, essentially. Okay. So we're going to start out with an increase in sympathetic activity. So that's the sympathetic branch of your autonomic part of your nervous system. And we're now thinking about specifically the parts that are going to veins. So when we have an increase in that sympathetic activity, that means those postganglionic sympathetic nerves, they're giving out their norepinephrine. Just mentioned, that's going to be binding to alpha receptors in the smooth muscle in the walls of our veins. When it does that, we say it increases venomotor tone, which is basically we're saying that we're constricting those walls a little bit. We just don't use the word vasoconstriction for veins, really. We talk about the venomotor tone because what we're focused on is compliance rather than resistance. Okay. So when we have that constriction in the smooth muscle, we increase the venomotor tone. It's decreasing our venous compliance, meaning that they can hold less volume for a given pressure. So if they keep that same volume, they're going to have a higher pressure. Okay? So we could follow along the curve that way. So questions to this point, because I feel like I've been talking a little fast. Okay. So we're going to move forward. Okay. So this is just adding on some other things that are going on with the veins at the same time. So at the same time as we have these increases in sympathetic nerves, increasing venomotor tone, decreasing compliance, overall our effect is that we're increasing the pressure in the veins because compliance has to do with that relationship between volume and pressure. So decreasing the compliance essentially increases the pressure. We have other things that are increasing the pressure at the same time. All right, so we have the activity of that skeletal muscle pump, pumping blood back to the veins, pumping it up. We have the activity of the respiratory pump, essentially sucking blood towards the heart with that drop in thoracic pressure. And we usually have increases in blood volume going along at the same time. Okay. So this is because we're all leading to our understanding of how we're changing our mean arterial pressure. So all of these things could kind of go together. So once we have that increase in venous pressure, this means that we are going to increase venous return to the heart, right? Because everything's working along pressure gradients. So you have your heart, blood is going to the right atrium from our veins. Okay. I'm gonna put on our vena cava. We got inferior vena cava, we got superior vena cava. Okay. So if we're creating high pressure in the veins during diastole, so that resting phase for your heart, you start out with low pressure in the right atrium because it doesn't have blood in it. All right, so this is creating that filling of the right atrium. When we have higher venous pressure, this is why we're saying that we're increasing venous return, right? Because we're increasing this effect, right? We're affecting that gradient. So as we do that, okay, so we're increasing the venous return. This means we had high pressure in the veins, we had lower pressure in the right atrium, so more blood flows to the right atrium. So we then are going to see, pull off that, okay? So after we have that blood move, we're now going to have higher atrial pressure because we had essentially more blood go because we had that higher gradient, okay? So we now have high pressure in the right atrium. Okay. So because of that high atrial pressure, we would end up with high end diastolic pressure and high end diastolic volume. So these are just the measures of how much blood we have in the heart at the end of diastole, so at the end of its filling phase, and a related pressure, that end diastolic pressure, which we sometimes call preload, is related to that increase in volume, essentially. And so we put more blood in the heart, meaning we have more volume and more pressure in the heart, ultimately. These are two factors that affect our stroke volume. So when we have more blood in the heart, more end diastolic volume, that means we have more blood to squeeze out when our heart contracts during systole. So we increase our stroke volume at the same time. Okay. So we had high pressure in the veins, means we put more blood into the heart as it filled. Because there's more blood in there, we can squeeze more blood out, so we increase our stroke volume. Overall, this means we have a higher cardiac output because cardiac output is dependent on stroke volume. And then we would add in heart rate so that it's per minute. We got volume per minute. Okay, so what we've done here is increase cardiac output by increasing stroke volume. Okay. Okay. And then this total effect is going to be to raise our mean arterial pressure, which is going to be dependent on that increase in cardiac output, which intuitively hopefully makes a little bit of sense, right? The mean arterial pressure is the pressure in the arteries. If you squeeze more blood into the arteries per minute, they're going to have higher pressure, all else being equal. So this is a very long way to say that we can change factors relating to our veins in order to change our mean arterial pressure, which is kind of a measure of blood pressure. Which means we are going to move directly into talking about lymph and regulation of that mean arterial pressure. We have pretty much one or two words to say about the lymph. So really, this is mostly talking about these pressures. Our quick word to say about this lymphatic system is that we do have another series of tubes that are not our arteries, arterioles, capillaries, venules, and veins going back to the heart. So we saw in our capillaries, as we were talking about net filtration, that we are actually overall filtering out more fluid than that venule end of our capillary is soaking back up, which means without the lymphatic system, we would be losing a lot of fluid into the tissue, swelling it up and not really having any way to return that to our cardiovascular system, which would be bad. It would mean we would be having dropping blood volumes and therefore, as we just traced, dropping blood pressure. Okay, so the lymphatic system is important for reasons of blood pressure there. You'll also talk about the lymphatic system if you go in detail thinking about the immune system. We'll see it again when we talk about our digestive system as well, because the lymphatic system is part of the way that we get fats out of our food. Okay, so the lymphatic system looks pretty much like our cardiovascular system. I would say it's analogous essentially to our veins, kind of. So we're going to have a system of vessels. Nodes are going to be specific to our lymphatic system, and we'll have some lymphatic organs as well. So what we're thinking about right now is that they are returning our excess filtrates, our excess fluid that we filtered out of our capillaries to our circulation. The way they do that is that they ultimately dump into your veins as your veins are going back to your heart. So specifically, the lymphatic veins drain into something called the thoracic duct, which is ultimately going to go into your right atrium. There's some variation in how that attaches in. I wouldn't say it goes directly to the right atrium. Overall, the lymph is just moving through the lymphatic veins the same way it would flow through regular veins. So those structures really do look the same pretty much. We also have immune effects in our lymphatic system. So specifically, we have macrophages located in our lymphatic system that are working on destroying pathogens. We'll talk about that when we talk about macrophages. So this is just a quick peek at how this works. Okay, so here we see our capillary bed. So we have our arteries, our arterioles, our capillaries, and our capillary bed. And we know that especially on that arterial side in the capillaries, we have lots of filtrate coming out. So lots of fluid going towards the capillaries. And on net, that is overall what's happening in our capillary beds, even though at the venule end, we have a little bit of absorption. Fortunately, we have lymphatic capillaries as well. So those lymphatic capillaries ultimately are going to catch some of that excess fluid that we've filtered out, pull it into our lymphatic system, and then it's going to flow all the way back up. Oh, I went too far. Going to flow all the way back up. It's going to dump into our veins, which then return that fluid back to the heart. So like our venous system, we are going to have valves in lymphatic veins, lymphatic vessels. So for now, that's what we need to know about lymph. So that we have now covered all our little tubes carrying fluid in the body. Okay. So now we're going to go back to thinking about pressure. So we had a couple equations that we've been working with, right? So we've been talking about our flow equivalent to a difference in pressure and a difference in, and our resistance overall. This is the equation I like to remember because I find it easiest to then just substitute things in here. So if we're thinking about the cardiovascular system, we know that the flow, the relevant flow is blood flow. So our blood flow through the cardiovascular system is our cardiac output. Okay. When we think about our difference in pressure, what we're really talking about is the difference in pressure between our arteries and our veins. That's our pressure gradient, our relevant pressure gradient. So that's our mean arterial pressure technically minus our central venous pressure, which is why we just saw that we could have effects on mean arterial pressure by changing properties of our veins. Usually when we're looking at this equation, we can ignore that central venous pressure because it's negligible. So it's near zero. But if we have changes to the veins, we do have to take it into account. And when we're thinking about our resistance, we're just thinking about adding up all the resistance out in your body. So our resistance is our total peripheral resistance. So once we substitute in these variables, we can start to reshape the equation to focus on any specific part of it we want to focus on. For now, since we're not talking about the veins anymore, I am going to cross out our central venous pressure just to make our reshaping of this equation easier. Unless we're talking about changes to the veins, we don't need to think about this. Okay. So now we have that our cardiac output is approximately equal to our mean arterial pressure divided by our total peripheral resistance. So we can move that total peripheral resistance over so that we are isolating our mean arterial pressure, which means we'd get mean arterial pressure equivalent to cardiac output times our resistance. And we could break it down even further with what we know about cardiac output. So we get mean arterial pressure equivalent to our stroke volume times our heart rate times our total peripheral resistance. So this is why I like to remember this first equation and then just substitute things and move stuff around. I find it easier than remembering a lot of bullet points. So recommend trying it that way. But otherwise, we could just look at this slide and see that our mean arterial pressure is dependent on heart rate, stroke volume, and total peripheral resistance, which is exactly what we got by reshaping this equation or reshaping this relationship. Okay. So this means that we can change our mean arterial pressure or regulate it by changing any of these variables, right? So we already know some factors that can change our stroke volume, that can change our heart rate. And we've talked about factors that can change the resistance, especially in our arterioles, right? So anything that's going to affect these three factors is going to be able to help us regulate our mean arterial pressure, right? Because if we have a change in any one of those variables, unless we have an equal and opposite change somewhere else, we'll overall change our mean arterial pressure. This means we'll be thinking about how our nerves affect these factors, as well as how our hormones affect these factors. The thing that we're going to have to add on as we're thinking about the regulation of mean arterial pressure is, when do we do it? Why do we do it? So here's where we are going to think about some sensors in the body. Specifically, we're going to be thinking about low pressure baroreceptors, which we can also think of as volume receptors. So these are going to be kind of our trigger for telling us what's going on with the mean arterial pressure. Cool. So right now, we're looking at a picture to just kind of try and conceptually, again, give you a way of thinking about what's going on with changes in mean arterial pressure. So if you don't like those equations or bullet points, maybe this will help kind of internalize it. So what we're looking at here, right, is we know that we have blood coming from our heart, right? Our cardiac output is coming from our heart. We measure mean arterial pressure in the aorta, so we're looking at the aorta. So if we just have constant blood flow in the heart and we don't have any changes in our total peripheral resistance, mainly due to our arterioles, if everything's just staying normal, we're going to have a constant pressure here in the aorta, essentially, okay, or a constant mean arterial pressure. Okay. However, if we have changes to that cardiac output, right, so we're saying that we have an increase in cardiac output, we're having an increase of flow into the aorta, If we still have that same resistance at the other end, right, we're getting kind of a bottleneck here a little bit. So we're going to have an increase in pressure as that increased volume is pushing out farther on the walls, right? So if we increase the flow into the aorta, we're still controlling that flow out with our resistance, we're going to see an increase in pressure in this area as those walls bulge out further. We know that we have pretty low compliance here in our aorta, which means that that pressure is going to rise even with pretty slight changes in volume. Okay, so that's again just relating our cardiac output to our mean arterial pressure, to flow and resistance. Okay, so our resistance. So we can play with this another way too. So now instead of changing our flow, we're going to say, comparing to that first image, so up top A from the previous slide, we're going to say that we're going to have the same flow in here. All right, so we're not going to change our cardiac output, but instead what we're going to do is constrict down that outflow. So we're going to increase resistance by blocking off this flow more. So this is another way that we can increase mean arterial pressure because we're essentially backing blood up, right? It's getting kind of stuck in this middle region, right? So we're again having an increase in volume right here where we're measuring. So it's pushing out against those walls. And since it's pushing out against those walls, that's measured as a pressure, right? That's that push against the walls. So that's why changes to resistance also cause changes to pressure. So either changing the flow going in or the resistance resisting that flow on the opposite end can change this mean arterial pressure. Okay. So as we think about controlling mean arterial pressure, we're thinking about controlling that cardiac output, that flow in, or controlling that resistance at the other end that is resisting that flow, that's kind of blocking it, controlling it a little bit. So if we control our heart or our arterioles and the veins, and therefore the resistance, we can control our mean arterial pressure. We can do that through neural control, so our nerves, like we were talking about at the beginning of today, like our sympathetic nervous system, or hormones like epinephrine, right? So we want to remember, in addition, we saw that aorta picture somewhere else, right? We did see that aorta picture last semester because we were talking about the fact that pressure in the aorta after you have the blood pump out, so after we pump our stroke volume into the aorta during the ventricular ejection phase of the cardiac cycle, we're holding pressure in those walls. And that's good because your heart relaxes. We no longer have cardiac output, like we no longer have stroke volume, I should say, an independent beat going in. So we can then release that pressure to continue to allow constant blood flow into the cardiovascular system. So maintaining that pressure here in the aorta is important, right? So regulating mean arterial pressure is going to be critical to normal function in your body. When we have pressures that are too low, so if mean arterial pressure is too low, this is going to be referred to as hypotension. So when you see tension, pressure, think about those as related concepts, right? Tension and pressure. Hypo meaning low, right? So that's our root for low. So if we have low blood pressure, this means we're not going to get enough blood flow to tissues. We may see drops in oxygen. We may see rises in carbon dioxide, right? So this is actually palpable, right? You can actually feel this difference if your blood pressure gets too low. You ever gotten too woozy when you stand up, right? Or you haven't had enough water, things like that, anything that drops your blood pressure, right? You've felt that low blood flow to your brain. Conversely, if you have mean arterial pressure that's too high, so higher than normal blood pressure, would be hyper, so too much tension, so too much pressure. This essentially is a stressor on your body. So the reason high blood pressure is a problem isn't that you're going to walk around and feel it suddenly hit you in the hallway at one single moment. It's that this is a long-term stress on your heart and on your blood vessels, right? Those blood vessel walls are having to resist that higher pressure, and long-term resisting that higher pressure for a long time actually does have effects on the walls of the blood vessels themselves. And your heart, if you have this high pressure, right, your heart has to go into the aorta. Right, so we have our aorta coming out of our heart, right? So if you have a high pressure here, afterload, actually, high pressure here, as you try to pump blood into that aorta, it's harder. The muscle has to work harder, right? Has to work harder to get blood out of the heart. That's stressful for your heart and can cause heart problems. So too high pressure, too low pressure, problem. So just discuss, hopefully you can pick out the 3 things that you would need to know in order to determine mean arterial pressure. Okay. So we talked about all of these words independently, but one of them in total is going to give us our mean arterial pressure. All the others are missing some factor. Hopefully we're getting that we're thinking about heart rate and stroke volume, which together are cardiac output. So B there, it's like saying the same thing double. We also need our total peripheral resistance, that blocking on the other end, because that's going to be important for figuring out how much pressure is building up. All right. So now we're going to think about short-term regulation and long-term regulation, because we're thinking about different effects when we're thinking about, okay, how do we stand up and not get lightheaded versus how do we not overall walk around with long-term stress on our heart from too high blood pressure, or how do we not have like long-term too low blood flow to our tissue. Right. So when we think about short-term regulation, we're thinking on the order of like seconds to minutes, right? That's what we mean by short here. So this is going to be mainly where we're focusing in this unit, because this is going to occur by regulating our cardiac output and our total peripheral resistance. So those factors we've just been talking about. So we're going to be controlling the heart and the blood vessels. And mainly this is going to be under neural control. So neural control, mostly our nerves are going to be making this short-term regulatory effect. In terms of long-term regulation, this is a little more tricky. So long-term regulation is going to occur on the order of minutes to days, so longer term. Okay? And this is mainly going to happen by regulating your blood volume. So this goes back a little bit to those notes about veins, that if we have more or less blood volume in a vein, it does change the pressure and therefore venous return to the heart. We actually regulate blood volume by controlling the kidneys. Okay? So we'll talk more about how that works when we get to our renal unit, which is unit 3. But this is largely going to be under control of different hormones that regulate basically kind of how much water you keep in your blood and therefore how much blood is in your cardiovascular system. Okay. So we're going to start by talking about our neural control of mean arterial pressure. So really, this is going to be a bunch of negative feedback loops. So your detectors, actually, I should say this is a homeostatic mechanism, right? So blood pressure is a regulated variable, right? So it's going to have its set point, right? We're going to detect error signals if we move away from that set point. And our detector, our sensor here, is going to be our baroreceptor. So baro, like a barometer, measures pressure. So a baroreceptor is a receptor for pressure. Okay. So when we were talking about homeostasis way back in the day, we talked about the fact that we're going to have a sensor out in the body. Then we're going to have a signal going to an integration center, an integrating center. So in your brainstem, you have cardiovascular centers that process this information and create a response. Okay. So that response is going to come out through your autonomic nervous system. Okay. That response, those are your controllers. And then our effector organs that actually change things in order to change our initial error signal are going to be our heart and blood vessels. So we're going to use our heart, change factors affecting our heart to change that cardiac output, stroke volume, and heart rate. And we're going to affect our blood vessels, largely that total peripheral resistance, in order to change our mean arterial pressure. Okay. So we're going to dial in on those baroreceptors. So our baroreceptors sense pressure. That's what that baro root is. Sometimes we call them stretch receptors as well, because of the way they function. Basically, they kind of like feel stretch, right? So we see arterial baroreceptors in the aortic arch. Okay. So in the arch of the aorta, we have some right here. So that's great, right? Because we know cardiac output is going directly into the aorta. So that's a good place to measure it. Arterial baroreceptor. The other place we want to have them, really important that you're getting enough blood, you have enough pressure going up to your brain. So we also have arterial baroreceptors in the carotid sinuses. So those are located basically at the split of your carotid arteries as they're going up through your neck and towards your brain. So sometimes we call them sino-aortic receptors. Sino for the carotid sinus, aortic for the aorta. So those are the two places we'd see baroreceptors in our arteries. So when they sense stretch of those walls is a measure of the pressure inside the blood vessel, as we just saw, because the pressure is formed as we have fluid pushing out on those walls. So we are going to, we're going to start on the next slide next time. You don't need to know much about the cardiovascular control center, other than the baroreceptors are signaling to them. They're in the brainstem, specifically the medulla oblongata. This is where we have our center for regulating blood pressure. So next time we'll start to talk about the factors we're changing to change these effects. So do remember we have a short quiz for Monday that'll go live at about 1, I think it's timed for. And otherwise have a great